We're nearing the end of this video lecture series on this example of the OMAE barge. The next step is to estimate the wet natural frequencies and modes. This is totally optional. One doesn't need to do this, but one might need to, and so I wanted to demonstrate it. It's very simple, but there were some things about it I wanted to talk about. I think this video will be relatively short. First of all, what are we talking about here? If we open up the lecture on the equations of hydroelasticity, in one of the slides we talked about wet natural frequencies and modes. This is essentially the equation we're going to be solving, except we're solving it in the reduced basis. So we're talking about Ks star, Kf star, Ms star, Mf star, and we want to solve this eigenvalue problem for the wet natural frequencies in this case because we're including Kf and Mf. But the process is Mf star is a function of frequency. So we have a series of frequencies. In this particular example, we have 67 frequencies. So we have 67 different values for M sub f. And so for each one of those, we solve this eigenvalue equation. And it's an 18 by 18. So there's 18 eigenvalues and more mode shapes in this for each frequency. And we look at the frequencies we calculate, the eigenvalues that we calculate, and we see how close they are to the wave frequency on which MF was calculated for each of these 67 wave frequencies. And then we look at this error equation down here where we say, okay, for each of those, for a given omega q, the wave frequency, we look at this difference here between the calculated natural frequencies and the wave frequency, and if that's within some tolerance, we're going to say, okay, that's a pretty good estimate of a wet natural frequency. And of course, the eigenvector would be an estimate of the wet mode, represented in terms of the reduced basis. So let us look at the input file for this, and it's very simple. To say the least. Come to BBEdit here, and this is it. First, we have to read the database that contains the stiffnesses and the hydrodynamic coefficient, added mass and damping. And then we use the command hide wet, and we need to use a shift here. And this is one doesn't really need to worry about this too much. I mean, one needs to do it because we've got this structure which has say 0 stiffness in the surge, sway, and yaw directions. So we do need to have a shift, and a value of 1 almost always seems to work for me. And then I'm saying, okay, the error, if the error was within 1%, we're going to accept that approximation. And whatever, if you come here to let me search for that hide, or help hide wet. You can see what the parameters mean here. So we're going to go back to here. So that's it. So let's look at the output we get for this thing. Miss wet. And I'm just going to leave it here. I will expand it a little bit. File in. So it's done. So if you look at this, it's done before I ever did anything really. So it goes through for each wave frequency, and it does the calculation for calculates the natural frequency, or actually I should say the eigenvalues for that equation. And if any of those natural frequencies meet our criterion, that will be listed here. And there's none listed here, so it didn't find any wet natural frequencies within 2-second period or 3.14 frequency. So we come down here until we find one that seems to match. Here we go. We have a match. Around 3 seconds, there's a frequency that's within 0.706. That's pretty small error, and so I would say there's a good estimate. This is a good estimate of a wet natural frequency. To figure out what the mode is, one would have to look at the mode shapes that are calculated. And we go down, and we find another one here. This frequency number, by the way, just means it's the frequency number that's calculated for that eigenvalue problem. It's not related to the frequency of the wet natural frequency number. So 0.477, again, that's pretty small, so it's a good estimate or a good reasonable assumption that this is a wet natural frequency as well. And we scroll down, 0.15, it's getting even closer, so there's a good estimate that around 4.1 seconds there's a wet period. But we see here that 4.2 seconds, 0.491, it's likely that this is the same frequency and that this has a smaller error, so one would probably take this. But to really tell that, one would have to look at the mode and see if it's essentially the same mode. And we go on down and see if there's any more that are calculated or estimated, and we don't find any within the 1% error that we specified. That's a pretty small fine tolerance, so you know, one may want to use a larger one, depending on how interested you are in finding these wet natural frequencies. So the wet modes are, let me just copy this. I don't want to have to type it, so let me just. So these are the wet modes, but these are the wet modes for the last frequency, so you don't really want to take these. What you want is this guy here, and here this accumulates the wet modes for the frequencies that match our criterion. Similarly, where is it here? Well, this is going to be cut off. So, but anyway, I can finish the name. How do you spell it? Accumulate, I guess. Okay, spell that. There we go. So there were 4, right? So this has accumulated these guys. All right, so that's it. This is an optional step if you want to investigate the wet natural periods and mode shapes.